You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoy the podcast, please listen, subscribe, like, and share it with friends. Thank you. Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcast. I have Jack Brouwer, professor of mechanical and aerospace engineering, University of California, Irvine, and director of the NFCRC, the National Fuel Cell Research Center, and the Advanced Power and Energy Program. So, Jack, thanks for coming.
Thank you. It's nice to be here.
Yeah, from what I've heard, fuel cells are becoming ultra important, and there's a big race on to allow them to store more and more energy, and for less and less money. But what's your experience in that arena? What are you working on?
So I'm working on stationary fuel cell technology primarily, which is the technology that with zero pollutant emissions can be controlled to complement solar and wind power, and that can also be fueled by renewable fuels, and especially I'm interested in ultimately everything being powered by renewably produced hydrogen. And that's a way in which we could introduce 100% renewable energy into our grid and into society.
If you look at, something just occurred to me. If you think of hydrogen instead of just as a proton, or with an electron, or just as a proton, does that open up the idea of instead of something having to be hydrogen powered, it can be powered by something else that's, you could you can pull a hydrogen off of, or I don't know where I'm going with that, but the idea just.
In a fuel cell, hydrogen gas does electrochemically get converted into protons and electrons. So that's a natural process by which electricity actually is being produced by a fuel cell. And the ions, protons in this particular case, which is just an H+, right? Those ions have to exist inside of a certain phase. So something has to actually be able to accept the ion, the proton in this case, which is a proton-conducting membrane, typically for most popular fuel cells. If you are talking about splitting the atom, of course, then you're starting to talk about nuclear energy, and that's not what we're talking about here. We're talking about electrochemical energy, which is most akin to the type of energy that we're familiar with from batteries, right?
So yeah, no, I meant instead of just using hydrogen gas in a fuel cell,
right?
Some other molecule that has a hydrogen bonded to it that you could pull off. I didn't mean nuclear, but that's
okay, what I was and that's the second part of the question that you asked, which is essentially associated with how we might be able to carry something else around that we could strip the hydrogen out of. And as a matter of fact, that is the most common way that stationary fuel cell systems are operating today. They are operating primarily upon natural gas, which is mainly comprised of methane. And these stationary fuel cell systems essentially strip the hydrogen off of that methane and then use it to make electricity and heat in combined heat and power applications. And that's because natural gas is the most ubiquitous fuel that we can operate these fuel cell systems off of. All of these fuel cell systems also can operate off of hydrogen. It's just not widely available like natural gas is today.
The same as is a fuel cell the same as a battery? I know that's a really stupid question.
No, a fuel cell is quite different from a battery. And if you were to make a direct comparison, a system that is comprised of an electrolyzer that takes electricity in and splits water into hydrogen and oxygen, followed by hydrogen storage in a container, and followed by a fuel cell that takes the hydrogen out of the container and makes electricity and water again, that whole system that I just described would be pretty close to, in its function, a battery, which takes electricity in and gives electricity back out. Okay? So the fuel cell is the electricity production side of a hydrogen energy storage system, which acts like a battery with electricity in, electricity out.
Okay, got it. All right, well, that's a good clarification. Excellent.
Yeah. So fuel cells are often compared to batteries when they are used in transportation applications, because in transportation applications, you have two zero-emission options. And the one is to use rechargeable batteries, in which case you refuel the automobile by plugging it in and recharging the battery. In the hydrogen and fuel cell case, you refuel the fuel cell electric vehicle by pumping some hydrogen into the storage tank. And then in both cases, those are zero-emission vehicles. The one provides electric propulsion by electrochemical conversion of the hydrogen. The other one provides chemical propulsion by discharging the battery and sending it to electric.
So what are the current constraints on stationary fuel cells? What's the state of the art look like? What are some of the parameters, and what are you trying to achieve?
So stationary fuel cells today are pretty widely used in a few markets. California is one of the markets in which stationary fuel cells are widely. The Northeast is another region. Japan and Korea and Europe also comprise areas where a lot of stationary fuel cell systems are installed. There's over 300 megawatts of stationary fuel cell systems installed in California, over 400 in South Korea, and then many more in Japan and Europe. These locations are installing fuel cells primarily because they have a competitive advantage in comparison to the electric rates that exist in these markets. They also have been incentivized in not all of these, but most of these markets because they have zero criteria pollutant emissions. And so with a small incentive and high electric rates, stationary fuel cell systems are being used quite widely today. Today, they are primarily being used as baseload power generation behind the meter. What I mean by that is that a customer who has a lot of electricity demand would actually install this behind his meter to reduce his electric bill. Okay. In the future, though, I see them being used much more often throughout the grid network to replace the dispatchable generators that currently use fossil fuels. So what we'd like to see is that we have renewable gases that include biogases, but also renewable hydrogen. And this would become the ubiquitous fuel that is moved around in society. And then you'd use a whole bunch of wind, a whole bunch of solar, and then you'd complement it with something that you can turn on and off, turn up and down, which is the fuel cell.
So what are some of the drawbacks of the fuel cells that you're looking to implement versus what's out there right now?
So right now, fuel cells have to compete with the lower capital cost technologies like gas turbines and reciprocating engines that use a combustion process for producing electricity. And those are much cheaper, but they are less efficient and they produce criteria pollutant emissions. So they are the things that they contribute somewhat to air quality problems that we have in society. So higher capital cost than competing technologies is one of the big hurdles of stationary fuel cells and fuel cells for use in transportation applications today, because the internal combustion engine in the car is a lot cheaper than the batteries for a battery electric vehicle or than the fuel cells for a fuel cell other challenges for fuel cells include the availability of renewable fuel, because that's the direction we must go, is in the direction of using all renewable energy. And the fuels that are widely available in society are primarily petroleum products, natural gas, and coal. Those are the things that are widely used today. Fortunately for the battery electric vehicle, electricity supply is pretty ubiquitous already. And this is why, for example, this is one of the reasons why battery electric vehicles have been adopted in much larger numbers so far than fuel cell electric. Fuel cells have the additional hurdle of introducing more hydrogen fueling infrastructure.
Okay, got it. So what's your reconception of the fuel cell? What would make it more competitive with, turbines and other things that use fossil fuels in combustion?
Well, the main thing that I think has to be done is to have a reasonable part of the market. So market share is the main thing. There's a lot of companies that have already very significantly reduced the cost of these systems, and it's mainly number of systems that they can produce annually that would bring the cost down sufficient for them to become widely adopted. So we have companies like Bloom Energy that are producing a solid oxide fuel cell. This is a high temperature fuel cell that can, even at a 250 kilowatt size, okay, so this is a small commercial building size, produce electricity at 65% fuel to electricity conversion efficiency. So this is an efficiency that is higher than the very largest natural gas combined cycle plant, which is based on gas turbines and steam turbines. Okay, so even in small size classes, these fuel cells can be made very efficiently, and the costs have come down very substantially. And there are other types of fuel cells too that are being advanced by other companies. So Fuel Cell Energy, for example, is advancing a carbonate fuel cell, which also has very high efficiencies. They have some configurations that also get to about 60% fuel to electricity conversion efficiency, and they produce also a high quality heat stream. So if you have an industry, or if you have a cold winter and you need a heating demand to be met, you can have that met by the fuel cell too. And then finally, phosphoric acid fuel cell technology is being advanced by Doosan, and they have more than a 20-year history of advancing their cell and stack technology, and they also are producing those systems at costs that are almost an order of magnitude lower than when they first started building these systems. But the markets yet haven't fully monetized all the value that the fuel cell systems can bring. Okay, so some of the values include things like the low criteria pollutant emissions. So if you could get paid for reducing air quality problems, that would help. Or the reduction in greenhouse gas emissions, which only happens in some places where they are incentivized. And then finally, paying these kinds of distributed power generation systems for services rendered to complement solar and wind. So for example, if you could have a fuel cell system that would only operate at half power when the sun's going down and when the sun's going up, full power at night, and then to be off in the middle of the day, that would help the grid immensely. And fuel cell systems can do that today, but they aren't getting paid for doing that today. Okay, so they tend to be just installed behind the meter and let the customer reduce their load.
The efficiency, what's the limit of efficiency from combustion? That's, I guess, based on the Carnot cycle, and it's like, what, 19-20%? Or what's the theoretical efficiency of the current combustion system?
So you're right about the Carnot limit applying to all heat engines. And the limit changes depending upon the size and the temperature difference characteristics that you can establish in your combustion engine. And so what ends up happening inside of a car, for example, it's a small engine. And that small engine cannot maintain a super high combustion temperature and a super low heat rejection temperature. And because of that, it has a limit that's very close to the one you just stated. Between 20 and 30%. Okay, is the limit for that size engine, and that's due to Carnot constraint limits, right? The fact that you cannot have a super high combustion temperature and a super low cold temperature in your cycle. The size class that I mentioned for the fuel cells, less than 1 megawatt, have a similar constraint for engines, either gas turbines or reciprocating engines. Okay, any one of these combustion technologies that depends upon a Carnot cycle, a Carnot limited cycle, they also have constraints that are well below 35%, usually below 30% for electricity conversion at this scale, compared to the 60% and 65% that I just mentioned for the same size of a fuel cell. Okay. Now,
well, what's the quick question? What's the theoretical efficiency of a fuel cell? Are we anywhere close?
So the theoretical efficiency, So the theoretical efficiency of fuel cell systems gets into the 80% range. Okay, so it's like the high 70s, but it's governed by something that's totally different. You don't have to establish a temperature difference to get electricity or energy out of a fuel cell system. What you do rather is establish a chemical potential difference. So what you do is you make sure that there's only fuel on one side of the fuel cell and only oxidant or air on the other side of the fuel cell. And it's that chemical potential difference that makes electricity versus the temperature difference that makes mechanical work that can be converted into electricity in the heat engine. So it's a totally different driving force. And so what ends up limiting the fuel cell is not the Carnot efficiency at any given size, but it's the Nernst potential. And I could describe that to you, but it basically has to do with a chemical potential difference instead of a temperature difference. That makes sense?
Yeah, no, I understand. I know the name Nernst from
oh, cool.
Famous chemist. I don't know.
Yes, absolutely.
I couldn't describe it like you could. Okay.
Yeah. So that's what limits it.
So the efficiency is pretty good. It could be better. And then the use of it, like you said, not used at certain times. What about the conditions in which a fuel cell can operate versus like a combustion scheme? Are they any different? Is one more robust than the other?
So the fuel cell systems that have been introduced in these applications, both in automobiles and in stationary power plants, have been very reliable. Their reliability record is quite outstanding. There also is less of a derate when you install at altitude or even operate them, for example, on board aircraft and stuff like that. So I think they will be found to be quite robust in most of these end uses and to be at least as reliable as the internal combustion engines that are much more popular and have been advanced for over 100 years. One of the reasons I would suggest that they would become even more reliable is because they have many fewer moving parts. So the main energy conversion component of a fuel cell system is the stack of fuel cells, which has no moving parts at all. So it ends up being much more like a battery in that sense, that it has no moving parts but makes electricity.
Well, it may not have moving parts, but I mean, there's fluids moving around in it, and I would think that sedimentation would build up in certain parts of it, or is that not the case?
Fuel cells, if you didn't have, let's say, filters on the air going in, or something that would protect, major dust elements getting in, yes, they could have a problem with things like that. But the exact same sort of filter that you already put, like on your car, is all you need. You don't need anything new or special in that regard. And so I don't think you'd find them to be more susceptible to either contaminants or to dust or other things accumulating than your current internal combustion engines are.
All right, but what about temperature ranges?
Yes.
Could a combustion scheme work underwater, but this couldn't?
Yeah, so that's an interesting.
What about at altitude?
Question.
That kind of stuff.
Yeah. In the early years, proton exchange membrane fuel cells, which are the main fuel cells used in automobile applications, because they require some water to be present in the proton exchange membrane itself for it to function properly, they had some challenges with freezing conditions, for example. or super dry atmospheric conditions like you might experience when driving through the desert. Okay. And all the automobile companies that invested in fuel cell automobiles, they invested quite a bit of time and effort taking the cars up to Alaska and driving them through Arizona over the years and introducing innovations at the system level that keep the membrane moist even when you're under these kinds of conditions, and that allow freezing and even totally frozen startup. And Honda, Toyota, Hyundai, everyone that's delivering a fuel cell vehicle now certifies them for exactly the same operating ranges as they do for internal combustion engines. So you can drive them all the way up to the same altitude, Pikes Peak and everything. You can operate them in any one of the environments that you operate an internal combustion engine in, and it's certified all the way down from like minus 40 to plus 120 or something like that Fahrenheit. So these sorts of things were big challenges with fuel cells in the early years, but they've been pretty much completely overcome by innovations at the automobile companies, at least.
How do fuel cells work, diurnally? If the temperature swings 30 degrees between day and night, the humidity goes from, I don't know, 80% to 20%. Does that change the pH of anything going on in the cell? Does it change the operating conditions, the efficiency? Like, how do they respond to natural?
Yeah, so that's interesting. Remember that the fuel cell depends upon a chemical potential difference and doesn't depend upon a temperature difference to do useful work, to produce the electricity. As a result, they're actually less susceptible to temperature changes than traditional energy conversion technologies. They are, however, susceptible to the concentration of the fuel on the fuel side and the concentration of oxygen on the air side. So if you think about high humidity conditions, you're going to be introducing more and more water into the oxidant side, and that will reduce the chemical potential difference that is experienced by the fuel cell and will have an efficiency impact. So low humidity conditions would lead to better efficiency. Okay. It is a very small amount of efficiency penalty, though, that is associated with that lower concentration of oxygen in the air.
Okay. But it's not a big swing, depending on.
No, it's not a big swing at all. And again, it's because of the fundamental dependence of fuel cells on the chemical potential difference rather than the temperature difference to produce the electricity.
Okay, excellent. So the mechanism, the chemicals used, where is the innovation going to come from, do you believe? Just more widespread adoption, or is it, where is it going to come from?
Yeah, let me mention a number of things that I think are going to be important over this next decade with regard to fuel cell technology for stationary applications first, and then maybe also in automobiles. The first is that most of the fuel cell systems that are out there still can benefit from a very significant investment in the balance of plant to reduce the part count, eliminate sensors, and eliminate valves and other things that are the main aspects of stationary fuel cell systems that actually lead to failure. It's not the inherent electrochemical production that occurs in the stack that usually fails. It's usually one of these smaller balance of plant components. And interestingly, one of the biggest accomplishments of the stationary fuel cell manufacturers, Doosan, Bloom, and Fuel Cell Energy, is to do these kinds of things up to this point, is to get the cost out, get the components out, and make the balance of plant more reliable. It's not necessarily brand new materials for the fuel cell stack or new kinds of innovations at the stack level. It's mostly how do I make a system that now is going to last for a long time and produce reliably. But there's a lot of system component details there, right? There's things like heat exchangers and valves and components for sealing and for doing all these kinds of things. Those kinds of things are I think, where the big savings and reliability improvements are going to come. Because I think we already know that we're going to use these 4 types of fuel cell systems primarily, right? There's going to be primarily proton exchange membrane, and that's the stack technology we're talking about in every case. There's going to be solid oxide, there's going to be carbonate, there's going to be phosphoric acid. And these are pretty mature with regard to stack technology. They just have to get the systems into this mass manufacturing and reduced cost mode.
So it's the ancillary support systems, not the guts of the fuel cell itself that need to be improved.
Yes. And when you only order 100 pumps, you still pay like full retail for them. They got to start ordering thousands of them, okay? And they're not doing that yet today. So this is the commercialization cost reduction that can happen naturally if the market grows, right?
So how do you use the excitement?
Let me mention one thing in particular, though, that's associated with the proton exchange membrane and the automobile use, because though the automobile manufacturers, together with scientists from around the world, have also reduced the cost of those engines very substantially. The one thing that I would suggest is remaining is to lower the amount of platinum that they use sufficiently. Now, again, this platinum issue is for the vehicle use, right? It's not for all these stationary uses, okay? And that's going to require some, I think, pretty fundamental research and development to continuously reduce the amount of platinum that is needed for good performance. Fortunately, we have good scientists around the world, and even right here at the National Fuel Cell Research Center, that are working on that kind of stuff. How do we reduce that platinum loading?
Why? Just because it's so precious, platinum, or is it create a waste product that's terrible?
Okay, it doesn't create a waste product that's terrible. As a matter of fact, it can be recycled quite readily and is being recycled from old fuel cell systems right now. Okay, but it's just so precious because it's a precious metal. It costs so much.
Okay.
Yeah.
It's funny that suggests that platinum is used in an engine that instead of someone buying a vehicle with the engine, they buy the vehicle, but they only can lease the engine. The engine must be returned at end of life to the manufacturer. Maybe that would help reduce the platinum demand because it's so precious.
Yes. You may know that this sort of thing is already happening with the catalytic converters. Platinum is being recovered from them and reintroduced to the market for automobiles. But you're correct. There's a little twist on the ownership and the end of life recovery that should be introduced for fuel cell electric vehicles, exactly like you just described. Yeah.
Maybe the whole car itself at some point will become you can't own it. You just are leasing it because it all has to be returned for reclamation.
Yes.
If you get a whole bunch of batteries and the catalytic converter and then the onboard fuel cells and the engine, I mean, the whole car then becomes a very valuable, recoverable source of materials.
And I know that the car companies are almost all of them. I know in particular Toyota has shared their plans with me for making the cars 90 to 100% recyclable. Okay, and so they're already looking at making everything recyclable on the car. So
yeah, that's great. You literally drive it into the ground, so there's nothing left.
Yeah, drive it into another car or something.
Yeah.
Make the next generation of car from your old car.
Would you mind just briefly going over the 4 technologies you talked about? Like proton membranes. How do they work? Just in brief, and then the other 3.
Yeah. So proton exchange membrane fuel cell has a polymer membrane that typically also takes in some water to allow protons to have some conductivity across that membrane. So it allows protons to go across, but not electrons or anything else, no gases. And so what happens is hydrogen breaks down on the anode side, making electrons and protons that go into the membrane, and then air goes into the opposite electrode and consumes electrons and has oxygen meet up with those protons to make water, leading to the fact that making electrons on the one side, consuming them on the other side, leads to a flow of electric current that is useful for driving a motor, powering a light, whatever. And so this is a polymer membrane that is mainly used. Phosphoric acid fuel cells use a matrix that supports a phosphoric acid water solution. Okay, so inside of the two electrodes, pardon?
I was joking, like a soda. Anyway,
yeah, it is like a soda, except for it's really phosphoric acid with some water. But that phosphoric acid allows also protons to become available in sufficient quantity inside of that liquid. And then with the continuous production of those protons on the anode and the continuous consumption of those protons on the cathode, it leads to a flow of protons across the liquid, and again, making electrons on the anode side and consuming them on the cathode side, with hydrogen going in on the anode and air going in on the cathode. So this is a liquid-based fuel cell. Carbonate fuel cells, on the other hand, they actually have a high-temperature molten salts that are between the two electrodes. And those salts are carbonate salts, usually made with lithium, sodium, potassium, and those kinds of compounds, which are like lithium carbonate, sodium carbonate, potassium carbonate, okay, these kinds of things. And if you think about what can happen then is that CO3 double minus, not protons now, but CO3 double minus is the charge carrier in this molten salt. And so what happens in that kind of fuel cell is hydrogen goes in and it breaks it down, but meets up with the carbonate ion to form water and CO2. And that CO2 that's made on the anode side gets sent back around to the cathode side, which, when meeting up with oxygen and electrons, makes another CO3 double minus. Okay?
Okay.
So this is a carbonate fuel cell and how it works. It pumps CO3 double minus from the cathode side to the anode side instead of pumping protons from the anode side to the cathode. Okay. Again,
Gotcha.
Making electrons on one side, consuming them on the other. Okay. And then finally, the solid oxide fuel cell, it operates using a ceramic material as the ion conductor. And you have to make a very specific kind of ceramic that ends up having vacancies or O double minus holes in it. Okay, so it's often called defect chemistry, the chemistry that defines how you make these kinds of materials. But anyways, so you have to have a certain kind of ceramic, which at high enough temperature will have a lot of these vacancies and they will be mobile. So the idea there is that oxygen comes into the cathode, it breaks down by consuming electrons into O double minuses, which can go inside of the ceramic material, okay, and be conducted from the cathode side to the anode side. And then on the anode side, hydrogen meets up with that oxygen, those O double minuses, and produces electrons and water, okay? So that's how the main fuel cell types work electrochemically.
Okay. All right, got it.
I don't know if that was too much or not enough.
No, that was good. I mean, we talked about a lot of issues surrounding them. What needs to happen for more widespread adoption? So what's the timeline? Are companies reacting sluggishly to implementing fuel cells, or is there a lot of excitement about them, and therefore it's going to be pretty quick where the infrastructure and the ancillary technology is developed, to make them cost effective? Or what's the industry look like right now?
So my feeling is that the really exciting parts of hydrogen and fuel cells are associated with regions of the world that have as a goal to reach 100% renewable or 100% zero emissions energy in society. Okay, because it's when you get to these goals of trying to make it 100% renewable on the grid that you end up needing something like hydrogen for massive and seasonal energy storage. And then secondly, it's very difficult to make things like aircraft and ships and trains zero emissions using batteries, but you can do it with hydrogen. And so you start to think about like some difficult industry and heavy duty transportation and the grid at 100% renewables. That's when hydrogen and fuel cells have their very best contributions to make. And so in the state of California, in Europe, in Japan, people are getting very excited about hydrogen and fuel cell technology because they know they need it to reach these kinds of policy goals. And so in these areas, we're starting to see already, for example, the stationary fuel cell systems that I talked about earlier, right? That we're installing, we have over 300 megawatts installed in California. There's over 400 in South Korea. There's about the same in Japan and about the same in Europe. And then we're also seeing hydrogen fueling stations being introduced in California. We have about 60 of them right now in our state. And anyone who needs rapid fueling, long range, or heavy payload in their transportation application, hydrogen can beat out batteries in those kinds of needs, right? There's another application that I haven't talked about that I think I need to introduce here, and that's the forklift. Yeah, that's the forklift application, because they're very popular in 24/7 materials handling applications. So, big distribution centers for, companies like FedEx and Walmart and all the big box stores and everything like that. They're starting to use hydrogen and fuel cells for zero emissions and high productivity, because you can fuel it super fast, unlike the battery forklifts, and they still have zero emissions. So you can keep them running 24/7, and you don't have to take out a whole shift for just charging the forklift. You just keep using them. So it's these kinds of things.
Okay.
When you really need zero emissions and you want to do it all the way and you want to do it throughout society, that hydrogen and fuel cells are going to make the biggest difference. And it's in these places where they're thinking about that where I think the most rapid advancement will occur. That's why we already have 60 fueling stations in California and about 6,000 fuel cell vehicles already operating in the state.
What about the hydrogen itself? What are the possible sources? What are the sources right now, and what will be the most ubiquitous or cleanest or easiest sources to get it?
Make it? Let me start backwards, because the one that we absolutely must use and that will enable all of the things that I just talked about is electrolytic hydrogen. So in other words, using electrolyzers that are powered by solar, wind, and other renewable energy resources. Okay, so this is going to be the biggest amount of hydrogen and the most important source of hydrogen for the future that we all envision. But as we're going there, we have other ways in which we can make hydrogen too, which are actually and they include many different things, like biomass and biogas. Okay, because we have these biogas and biomass waste streams that we have to handle anyway. Well, one of the ways that we could handle them is to reduce them to solid carbon and hydrogen, okay? In which case you would have no CO2 emissions and you would have hydrogen that you can use in society. You also have ways in which you can actually directly anaerobically produce hydrogen using, biology, using certain types of bacteria, right? And you also can, at least today, with low cost, produce hydrogen from natural gas with very low emissions, and that's the main way we make it today. But one of the more exciting ones is what I want to talk about, because it's starting to become already pretty...
No, let's talk about the boring stuff.
Okay.
I'm just kidding. Go ahead. I'm kidding. Go ahead.
So one of the ones that's excitingly close to becoming very cost effective is to build your own solar farm, because solar power has become quite inexpensive, okay? And to connect that solar farm not up to the grid at all, so you avoid all interconnections with the grid and everything, but to connect it directly to an electrolyzer to produce hydrogen for fueling fuel cell vehicles.
That would take a lot of the burden it'll take the burden off a lot of infrastructure if you have hydrogen.
Yes, it takes the burden off of the infrastructure. Absolutely. Yeah. And you don't count on the grid to manage your solar. You don't have to count on new pipelines going in to bring the hydrogen somewhere else. You just put it where you need it, and you have this. Okay. And it's still a little too expensive compared to making the hydrogen from natural gas and shipping it, but it's close now, and that's why it's exciting.
Well, in remote areas, ironically, maybe the first place this will be is in remote third world countries, in remote areas where, it's a little bit more expensive, but you don't have to transport it, which would be so expensive it would be infeasible, or just physically infeasible.
Yes, exactly. We published a paper a couple years ago that essentially talked about that, putting wind and solar resources right next to the fueling station and then having those run through an electrolyzer and power the compression equipment for totally handling the fueling of renewable hydrogen at a remote fueling station. So.
Well, very cool. What made this conversation good is your passion in, getting renewables out there and about fuel cells themselves and everything. So what's the best way for folks to learn more and maybe to get in contact?
Yes, they can learn more by going to the National Fuel Cell Research Center website, and that's at www.nfcrc.uci.edu. They also can email me. My email address is jb@nfcrc.uci.edu, and I'd be pleased to entertain questions from anyone.
Okay, well, very good. Well, Jack, I really appreciate you coming on the podcast. Thank you so much.
Thanks for your questions and interesting discussion.
You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you.